Welcome back to the Deep Dive, the place where we take your source materials, that heavy stack of research and notes, and distill them into clear, actionable knowledge.
And today, our mission is it's a masterclass in controlled chaos.
I like that. We are plunging into the world of mocking and patching software objects, which, it's really just the art of writing lightning-fast, highly reliable tests by embracing total isolation.
Total isolation is absolutely the key phrase there. The core problem we're trying to solve is really about diagnostics.
Diagnostics.
Yeah, think about it like this. If you have a complex system, let's stick with that analogy of a modern car engine, and it fails to start, you have this massive problem.
Right. Is it the battery, the starter,
Yeah,
something else entirely?
exactly. Is it the fuel pump, the onboard computer, a faulty sensor? When all those components are so deeply interconnected, diagnosing the single point of failure is, well, it's brutal.
So mocking is our shortcut.
It is. We use mocking to bypass all that complexity. It lets us test one tiny unit at a time. So if a test fails, you know exactly which spark plug is the culprit, because you made sure everything else was just a known stable fake.
Okay, so let's unpack that. Why on earth would we replace our robust, production-ready code with a deliberately fake object? Our sources point to two really critical motivations for this.
The first, and it's the most foundational one, is pure isolation.
Okay.
We have to isolate the unit we're testing from all its collaborating classes or functions. We just don't want the success or failure of, say, Unit A to depend on whether Unit B is talking to the network correctly.
So you stub out Unit B.
You stub out Unit B so you can get a laser-like focus on Unit A.
And the second reason sounds entirely pragmatic. It's about avoiding risk and expense.
Exactly. This is the real-world headache.
Yeah.
Think about objects that are complex to set up or tear down, or even worse, objects that have real side effects.
Like what?
Shared databases, interacting with a physical file system, calling a payment processor, or, communicating with cloud services like AWS or Google Cloud.
Right. You definitely do not want every single unit test run to cost you money.
Or require 30 seconds of setup, or, heaven forbid, accidentally modify production data. Mocks replace all those expensive, risky dependencies with a cheap, harmless stand-in.
And, we really know this pain firsthand,
Yeah.
especially when you're dealing with practical programming challenges. I'm thinking about those online contests or even just simple command line scripts.
Oh, yeah. If you write a function that takes input and prints output, you run into these testing obstacles immediately.
Like, how do you programmatically check what a function actually printed to the screen? You can't just look at it.
Right. And on the flip side, how do you automate feeding data into it without a human having to sit there typing and hitting enter over and over?
So mocking and patching are the advanced tools for that.
They're designed specifically to solve those input and output flow problems and make those challenges genuinely testable.
So let's start with the base tool itself. We're talking about Python's standard unitesting mock module and specifically the mock base class.
This is the foundation of our entire fake world. And there is one crucial rule when you substitute an object.
And that is?
The mock must maintain the interface of the real object it's replacing. So if the code you're testing expects to interact with the JSON library and it calls, say, json.dumps, then your mock object must also have a dumps method.
Or else the whole thing just crashes.
Immediately, you'll get an attribute error and the test stops.
But I don't have to manually define every single method on my mock object, do I? If the real object has 20 methods and my code only uses 3 of them, do I have to code all 20?
Not at all. And that's really the brilliance of the mock architecture. It operates under this policy of, let's call it extreme generosity.
Generosity.
It simulates objects by creating attributes and methods dynamically the moment they're accessed. So if your code calls mockObject.summerRandom method, the mock just says, sure, that exists now, and it creates it on the fly.
So it's kind of a digital shapeshifter. If I call a method on a mock, what does it give me back by default?
By default, every single method or attribute call on a basic mock object returns another brand new mock object.
So it's just mocks all the way down.
It creates an infinite depth of fakes. This lets the code under test explore these arbitrarily complex attribute chains without crashing. It's useful, but it also has a dark side we should probably talk about later. It can hide bugs.
I see. Okay. So it lets the code proceed, but then we have to keep track of what happened. Because these mock instances aren't just placeholders. They're more like audit trails.
Absolutely. The recording feature is the most potent part of the mock. Once you've run your test, you don't just check if the output was right, you inspect the mock to see how your code actually interacted with that dependency.
And what kind of information can we pull back from that audit trail?
There are a few key attributes for this. First, you have call count, which tells you exactly how many times the object or method was invoked.
Simple enough.
Then there's call args. That gives you a tuple of the arguments from the most recent call.
The most recent one, got it.
And finally, my personal favorite for complex interactions is method calls. It gives you a chronological list of every method called on the object and what arguments were passed to each one.
Wow, that usage data is incredible.
Yeah.
Because it lets you assert not just that something ran, but that it ran with the right inputs and in the correct sequence.
Exactly. And that ability to verify sequence and input is key to reliability, but verification is only half the story. We also need control.
Right, because if the mock just returns another mock, our function might not be able to do anything useful. We have to tell it what concrete data to return.
Precisely. If the real object returns a list of users, the fake has to return a fake list of users, so our code can process it.
So how do we program that predetermined behavior?
The primary way is with the return value attribute. You just said it, and every time the mock is called, that is the value it will reliably return. Let's use that classic example from the sources. Testing a function that depends on the day of the week.
Okay, yeah. So if the function calls datetime.today, its behavior is non-deterministic. If I run the test on a Monday, it passes, but maybe if I run it on a Sunday, it fails.
Precisely. We need to freeze time. So we mark the datetime module, and we set the return value for its today method to be a pre-selected date, say Wednesday, January 10th, 2024.
And now, no matter when I run that test.
Your function will always believe it is a Wednesday. It makes your test deterministic and repeatable. That predictability is the real win here.
But what if our code needs to make multiple calls and we expect a different result each time? Like the first call succeeds, the second fails, and the third returns nothing.
That is where we turn off return value and we introduce the side effect parameter.
Side effect.
Instead of one single return value, side effect specifies a sequence of actions. You can pass it a list of values. The mock will then just return the next value in the sequence with each call until the list is exhausted.
That seems much more realistic for things like API paging or reading a few lines from a file.
It is. And here's where side effect gets really powerful for testing everything. You can also include exceptions in that list.
Ah, so you can test your error handling.
Exactly. If you want to simulate a network timeout on the second call, you just put timeout error into the side effect iterable. The mock will then dutifully raise that exception when it's called the second time.
Which lets you test your application's retry logic, all without ever touching a real network.
All without touching a network.
Okay, so we've mastered the mock object itself. It's a recorder, it's a controller, a stand-in. But what if the object we need to fake is, like, imported 3 layers deep into some other module? How do we surgically replace it?
That's a hard transition, and it's where we bring in the concept of patching. While mocks are the fakes, patch is the surgical tool we use to inject those fakes deep into the code base.
And that's also from unitest.mock.
Also provided by unitesting.mock, yeah.
So how does patch actually work? Is it rewriting the source code files?
No, it's much cleaner than that. Looks up a specific object by its name using Python's import path in a specific module, and it just temporarily replaces that object with a mock instance.
And then when the test is over,
It magically restores the original object. No harm done.
Now, I noticed in the source material that sometimes the patch uses a standard mock, but other times it uses something called magic mock. What's the difference there?
That's an excellent point, and it's really important for patching classes. Magic mock is basically a slightly more powerful version of mock.
How so?
It automatically implements all of Python's dunder or magic methods. These are the ones with the double underscores, like len, iter, and critically enter and exit.
Ah, okay. So if I'm mocking a file object or a database connection that's used inside a with statement, that relies on enter and exit.
Precisely. If you are patching a class that your code treats as a context manager, you need the fake to support those magic methods. Magic mock gives you that support automatically. It saves you a ton of work.
Okay, let's talk deployment. How do we apply this patch? Seems like we have a few options.
We do. There are 3 main ways. The most common is probably as a decorator. You use the patch module.objectorplace syntax right above your test function.
And that mocks it for the whole function.
For the entire duration of that function. And if you need to replace 5 things, you can just stack 5 decorators.
I can see how that could get messy. Stacking decorators can make it hard to read to see which patch maps to which argument.
And that frustration is exactly why we have the second method, as a context manager.
With statement.
Yeah, you just use with patch module.object as a mock name. It's clean, it's localized, it's perfect when you only need to mock something for, say, 3 lines of code in a longer test. When that with black exits, the patch is gone.
And then there's the really surgical option. What if I want the real object, but I just want to fake one single method on it?
That's targeted patching. You use patch.object, the class, the method name. This is incredibly useful for integration tests where, 99% of a class is fine, but one specific method, like a cleanup method, is too expensive to run.
So you replace only that one piece.
You replace only that single method, leaving the rest of the class totally intact.
Now, this brings us to what the sourcing called out as the single most common pitfall, and frankly, a place where I have definitely messed up before.
Yeah.
The critical rule of where to apply the patch.
This is the high-value takeaway of the whole dive. If you take one thing away, it should be this. You must patch the object where it is looked up, not where it is defined.
And why is that? Why does patching where it's defined fail? I mean, I define my database connection in dbconfig.py. Why can't I just patch it there?
Because of Python's import mechanism, if your system under test, let's call it myapp.py, imports that database connection before your test runs, myapp.py already has a reference to the real object in its own memory.
But when I patch the original file,
myapp.py doesn't care. It's still holding on to that original real connection. You have to patch myapp.db connection, the object as it's referenced in the module that's using it, for the substitution to actually work.
patch where it's used, not where it's defined.
That's the rule.
That distinction is so crucial. It's almost like trying to change an ingredient back at the factory, but the chef has already pulled the real ingredient out of the fridge and into his own kitchen.
That is a perfect analogy. You have to intervene at the point of consumption.
Let's loop back to those practical problems then.
Oh.
Standard input and output. How do we apply this to code that uses the native print or input functions?
Right. So if your function uses print or input, it's touching sys.pdout and sys.tdin. These are file streams, and they're messy to test. So we patch them using a utility called stringio.
Wait, what exactly is stringio?
It's a fantastic little utility. Stringio lets us treat a string in memory as if it were a file. It's readable, it's writable, you can seek through it just like a real file handle, but it all happens instantly in memory.
Okay, so let's walk through the FizzBuzz challenge. My FizzBuzz function calls print 100 times. How do I test that output?
Step 1. You patch sys.stdout with an instance of stringio. So now any calls to print will write to our little memory buffer instead of the console.
Okay.
Step 2. After you run FizzBuzz, you just read the entire contents of that stringio buffer. It's just a simple string with 100 lines of output.
And step 3 is just to assert that the string is correct.
You assert that string equals the known correct result for FizzBuzz. You've isolated the I/O, you've achieved control, and your test is now deterministic.
That takes a really hard testing problem and makes it almost trivial.
Yeah.
But we talked about the dark side of mocks earlier. If they're this flexible, they can give us a false sense of confidence, right?
Absolutely. The main risk is that test passes, production fails scenario. And the biggest culprit is interface changes and just simple misspellings.
How so?
Since a mock dynamically creates any method you call on it, if the real object changes its method name from save user to store user, your test might still call mock.saveuser.
And the mock just says, sure, I have that method now.
Exactly. The test passes, but the production code, which calls the real object, will crash because saved user doesn't exist anymore.
Wait, so we've designed a tool that's so flexible, it can actually let our production code be completely broken while our tests report 100% success. That feels dangerous.
It is. And that flexibility needs a leash. The other risk is relying on external dependencies that change. If an API you're faking updates its required parameters, your mock-based test will still pass because the mock doesn't enforce those rules.
But the real API will reject the call.
The second you deploy, it fails.
So how do we put safeguards on this?
Yeah.
How do we make sure our mock respects the actual interface of the real object?
The preventative measure is to use specifications, or the spec parameter. When you create your mock, you provide the actual class or module you're faking as the spec.
And what does that do?
You're essentially telling the mock you are only allowed to accept calls for methods or attributes that are actually listed in the real interface of this object.
So if the test then calls a misspelled method,
the test fails immediately, even though it's a mock. The mock loses its dynamic generosity and becomes a hard enforcer of the interface. It prevents those silent, dangerous false positives.
this constant tension between comprehensive testing and the inherent fallibility of code, it leads us to the philosophical end of our dive. We use these tools to push for high code coverage, but, as E.W. Dijkstra famously noted,
Program testing can be used to show the presence of bugs, but never to show their absence. It's a profound realization, you know? No matter how good your tests are, you can only prove a failure exists. You can never prove the code is perfect.
right, you can prove the floor is dirty, but you can't prove it's spotless just by looking at a few spots.
But despite that philosophical challenge, the practical goal remains. Mocking, patching, and other techniques like property-based testing, they're the tools that make getting to 100% code coverage feasible.
Because mocking lets you hit every single branch of your code.
Every single one, including all those tricky error paths and dependency failures, which makes your tests exponentially more valuable.
That was a tremendous deep dive. We went from the core need for isolation, mastered the mock as a recorder and controller, defined the role of magic mock, detailed the 3 modes of patch, and most importantly, established that golden rule.
Patch where it's looked up, not where it's defined.
Exactly.
And so here's the final provocation for you, the listener, to bridge that gap between theory and application. We specifically mentioned 2 common I/O-heavy programming challenges, FizzBuzz and mixed fractions.
Right, both require a lot of interaction with standard input and output, reading from one stream, printing to another.
Your challenge is this. Take the principles of stringio and patch we discussed today and really think about how you would structure a robust, reliable integration test for a complete solution to that mixed fractions problem.
How do you feed in complex numbers and assert the output sequence is correct?
All within a clean, deterministic test framework. That's where the real power of patching truly shines.
Go forth. Write deterministic tests. Use specs to avoid those phantom bugs and start testing your error states. Thank you for joining us for the deep dive.
We'll catch you next time.